Let us learn some more terms which are used in study of graphs. First one is eccentricity. We define eccentricity of a vertex. If V is any vertex in graph G, then eccentricity of A is denoted by E of V. It is a distance, it's a distance from the vertex V to the vertex which is farthest from V in graph G. It's a distance from vertex V to the vertex which is farthest from V in my graph G. That is, I can write it as eccentricity of V is nothing but maximum distance. Okay, it's maximum distance between Vi and V for all V belongs to G. It's a distance from V to the vertex which is farthest from V. If Vi is any vertex which is farthest from V, then the maximum distance between them gives me eccentricity. For example, if I consider first I'll take a tree, okay. If I consider this as vertex A, B, C, D, E, F, G, H, I, J. Now if I want to find eccentricity of say G, okay, eccentricity of vertex G. Now if I consider distance between G and J, it is 1, and even for K, D, it is distance is 1. If I take I, E and F, they are at distance 2 from G. Vertex I, vertex E and vertex F are at distance 2 from G, right? 1, 2, 1, 2, 1, 2. So next highest distance is 2. Now when I consider vertex C, it is at distance, again it is at distance 2. If I consider vertex A or B, then it is at distance 3. G from A, the distance is 3. Same from B. Therefore, eccentricity of G is 3. Okay. Similarly, you can find distances for rest also. I'll take one more graph. Draw something like this. Okay. I'll add up one more over here. Okay. This is my graph. Say A, B, C, D, E, F, G and H. Okay, now for this I'll mention the eccentricity of A. What is the eccentricity of A? It's a maximum distance from A to the vertex which is farthest from A. This is at distance 1. These two are at distance 2. This and this are at distance 3. And this vertex, if I consider, this is at distance 3. If I consider H, then this is at distance 4. 1, 2, 3. 1, 2, 3, 4. So eccentricity of A is 4. Similarly, eccentricity of B, if I consider, then it is 1, 2, 1, 2, 3 for this, from these two. So if I consider that is 3, then if I consider eccentricity of C, that is also 3. Similarly, eccentricity of D, this is only these two are at highest distance, so that is 2. Eccentricity of E, if I consider eccentricity of E, that is 3. Like that you can write eccentricity of F 3, eccentricity of G, if I consider, I guess it is 3, 1, 2, 3. Eccentricity of F, G, H, this and for this they are same, so eccentricity of H is 4. Like that, eccentricity of any vertex is a distance from a vertex, from that vertex to the vertex which is farthest from it. One more term, that is center of a graph or center of a tree. Center, which is nothing but the vertex with the minimum eccentricity. Here I have listed the eccentricities. Which vertex have got minimum eccentricity? That is nothing but the center. Center is a vertex with minimum eccentricity. For example, if I consider, here only I can mention, I guess, in this I have listed out all the eccentricities. So this vertex D is a center which has got minimum eccentricity. You can observe this G is at distance 1, B at distance 1, F at 1, E and C both are at distance 1, and the next is A and H, they are at distance 2. So this is a center of graph. There may be, it's not necessary that graph should have one center, okay, there may be two centers. I'll give one such example. Of course, I'm going to take a tree. Yeah, this is my tree now. A, B, C, D, E, F, G, H, I, J. Okay, now eccentricities I'll just list out. Eccentricity of A is 5. Eccentricity of B is 4. Eccentricity of C is 3. Then eccentricity of E is again 5, so which is same as eccentricity of E. Then eccentricity of eccentricity of D. Eccentricity of D is 4. Yeah, eccentricity of D is 4. Eccentricity of E is 5. I have mentioned A, B, C, D, E, F. Eccentricity of F. Eccentricity of F is 3. Eccentricity of G is 4. I'm just writing it like this just to save the time. G, H, if I consider, yeah, it is again 5. So eccentricity of H is 5. Then eccentricity of I. I and J have got same eccentricity, so I, it is 4. Then eccentricity of J and H, J and H, yes, it is 5. So there are A, E, H and J, they have got maximum eccentricity. Minimum eccentricity is C and F. Therefore, you can observe C and F are the centers of this graph, are the centers. So that's what it is not necessary that you should get a single vertex as a center. And one more term, that is radius of a graph. The eccentricity of the center is nothing but, in tree in fact, eccentricity of a center in a tree is nothing but radius of a tree. Eccentricity of a center in a tree is nothing but radius of a tree. And one more term I'll mention and I'll give the example. Diameter of tree, diameter, that is, diameter of a tree is the length of the longest path in tree. Length of the longest path in tree is nothing but diameter. So of course the terms are based on trees. Take up. I'll draw something like this. I'll just directly write. What is the radius? Can you guess? What is the center for this? Is vertex 1, 2, 3, 4, 5, 6, 7, 8. Eccentricity, I'll list out. Eccentricity of 1. Vertex 1 is the maximum distance from 1 to the vertex which is farthest from this. So that is 8. So that has got length 3. So eccentricity of 1 is 3. Eccentricity of 2 is this 1, 2, 3, 4. Eccentricity of vertex 3 is 1, 2, 1, 2, 1, 2. So 1, 2, 3, 1, 2. So it is 3. Eccentricity of vertex 4 is 1, 2, 3, 4. Eccentricity of vertex 5 is 1, 2, 3, 4, 5. Eccentricity of vertex 6 is 1, 2, 3. Same as this. Eccentricity of vertex 7 is 1, 2, 3, 1, 2, 3, 4. So it's same as this. Eccentricity of vertex 8 is 1, 2, 3, 4, 5. That is eccentricity of vertex 8. So eccentricity, what is the center here? Center is a vertex with minimum eccentricity. Vertex with minimum eccentricity is vertex 3 and vertex 1. Vertex 1 and vertex 3. So center is this. So eccentricity of the center is nothing but the radius. So radius is 3 and diameter is nothing but length of the longest path. So that is, if I consider this 1 2 3 4, 1 2 3, 1 2 3 4, so that is 4. Sorry, it must be 5, because length of the highest eccentricity, highest eccentricity is nothing but the diameter. In fact, length of the longest path, so from this to this, if I consider 1 2 3 4 5, so it is 5. Now we can observe that every tree has either one or two centers. With the example, of course, we can easily prove, but how to prove theoretically? So I have a tree T, say let us take a tree T, more than two vertices are there in tree T. Let T be my tree with more than two vertices. More than two vertices. We know one thing, the maximum distance, okay, maximum distance d of v comma vi from a given vertex v to the vertex, any other vertex vi, occurs only when vi is a pendant vertex. Of course, we have observed in the previous example, if vi is a pendant vertex, then the distance between this vi and vi becomes the maximum. So the maximum distance d of v comma vi occurs only when vi is a pendant or a vertex. This happens only when vi is a pendant vertex. So what I'm doing is I'm taking a tree T with the number of vertices more than 2. Now we know tree must have at least 2 pendant vertices. Okay, I am going to delete all the pendant vertices from T. Okay, removing all the pendant vertices from T. So I am going to get new graph. We'll get a new graph, say T dash. New tree is formed, that is T dash. Now, if T dash is a tree, of course it will be a tree, because from a tree I am removing the pendant vertices. So T dash is also a tree, and even this has got few pendant vertices. Now what happens on removal of pendant vertices from T? Initially all the vertices, they have got some eccentricities. On removal of pendant vertices, eccentricities of all the vertices in T dash is reduced by 1, because I have removed the pendant vertices. So on removal of pendant vertices, eccentricities of remaining vertices, or eccentricities of vertices in T dash is reduced by 1. It's reduced by 1, or it is reduced by, it is 1 less than the eccentricities when they were in T. Okay, so the center will not change now. I have just removed the pendant vertices. Say some vertex was the center here in T. On removal of pendant vertices, eccentricities of all the vertices are reduced by 1. So center won't change. The center of T remains the same as the center of T dash. So center of T is same as center of T dash. It will not change. So from T dash now, what I do is, from T dash, again I am removing all the pendant vertices. all the pendant vertices. To get a new tree, say T double dash. I'll continue this process until I'm left with either a vertex or an edge. We'll continue this until there is either a vertex, there is left with either a vertex or an edge. Thus, original tree is reduced to a vertex or an edge. If it is reduced to a vertex, then it has got center 1. If it is reduced to an edge, then it has got 2 centers. If it is reduced to vertex, then only 1 center. If it is reduced to an edge, if it is reduced to an edge, then it has got 2 centers. Hence the proof. I'll explain once again. I have to prove every tree has either 1 or 2 centers. If I consider a tree T with more than 2 vertices, okay, of course, if I have considered more than 2 vertices, then I can say, tree T, I'm considering a tree T with more than 2 vertices. Now, maximum distance occurs only if vertex VI is a pendant vertex. What I am doing is I am removing all the pendant vertices from T. Now, new tree is formed, and in that eccentricities of all the vertices in T dash is 1 less than the vertices which are there in T. Okay, while coming from this to this step, eccentricities are reduced by 1. So this will not affect the center of T. So center of T is same as center of T dash. I'll continue this process from T dash. Again, I'm removing all the pendant vertices and I'm getting T double dash. So on, I'm continuing till I'm left with the vertex or an edge. If I left with an vertex, then it has got only 1 center. If I'm left with an edge, that means 2 vertex, therefore 2 centers. Next is types of trees. First one is rooted tree. It's a tree in which one vertex is distinguished from all other vertices. A tree in which one vertex is distinguished from all other vertices. Is called a rooted tree. For example, if this is my tree, this one vertex is distinguished from all other vertex, and this is called a root. And this tree is called rooted tree. Next is binary tree. Binary tree, it's a tree in which there is it's a tree in which there is exactly one vertex of degree 2 and the remaining vertices are of degree 1 or 3. Okay, it's a tree in which there is exactly one vertex of degree 2 and the remaining vertices are of degree 1 or 3. Okay, remaining vertices are of degree 1 or 3. For example, consider simply this. Then this is also binary tree, one vertex of degree 2. I can even write this. You can observe the vertices are of degree 1 or 3. 1 1 3 1 1 3, like that. It's not necessary that I should have one vertex of degree 2. Okay. Always remember one thing, binary tree is also a rooted tree. Okay, and we can consider the vertex of degree 2, this one such vertex of degree 2 as a root. We can observe few things in binary trees. One such thing is number of vertices in a binary tree is always odd. Number of vertices in a binary tree is always odd. Why? In a binary tree, I know one vertex is of degree 2. In binary tree, one vertex of degree 2. And the remaining n minus 1 vertices are of degree 1 or 3. Right? That means of odd degree. We already know that number of odd degree vertices in a graph is always even. Number of odd degree vertices is even, right? Therefore, there are n minus 1 vertices of odd degree. Therefore, this n minus 1 must be an even number. That implies n must be odd. Therefore, number of vertices in a binary tree is always odd. One more thing we can observe is how many pendant vertices are there in a binary tree with n vertices. It says number of pendant vertices is nothing but 1 plus number of vertices divided by 2. I'm considering a tree with n vertices and p pendant vertices. Okay, we know tree with n vertices will have n minus 1 edges, right? So total degree of T is 2 into number of edges, 2 into n minus 1, right? Now T has got n vertices. Among this n vertices, one vertex is of degree 2, one vertex of degree 2. Among n vertices of a tree T, one vertex is of degree 2. I have got p pendant vertices. So what is the degree of a pendant vertex? It is 1. So there are p pendant vertices of degree 1. And how many remains? How many vertices are remaining now? From n, 1 is of degree 2, p is of degree 1. So n minus p minus 1 vertices are left. Among n vertices, one vertex is of degree 2 because I have considered a binary tree now. So one vertex is of degree 2 and p is nothing but number of pendant vertices are of degree 1. So the remaining is n minus p minus 1 vertices are of degree 3, because we know a binary tree is a tree where one vertex is of degree 2 and the remaining vertices are of degree 1 or 3. Okay. So total degree becomes now, based on this, one vertex is of degree 2. So 1 into 2 plus p vertices are of degree 1 and n minus p minus 1 vertices are of degree 3. What is total degree? Total degree I have already considered. Tree with n vertices will have n minus 1 edges. So total degree is 2 into n minus 1. So it is 2 into n minus 1, which is equal to 2 plus p plus 3n minus 3p minus 3, which is nothing but 3n minus 2p minus 1. That implies this is 2n minus 2 if you want. Then I'm considering over here 2p is 3n minus 2n is n, and this comes here, so it is plus 1. Therefore p, number of pendant vertices, is nothing but number of vertices plus 1 divided by 2. So you may be asked, like, number of pendant vertices in a graph with 13 vertices, how many pendant vertices are there, like that. Such questions may be asked. So number of pendant vertices in a binary tree is n plus 1 divided by 2, where n is nothing but number of vertices. One more thing, vertices which are not pendant vertices are called internal vertices. Okay, if any vertex is not a pendant vertex, then it is called internal vertex of a tree. So based on that, how many internal vertices can be there in the binary tree, or in a tree in fact? Number of internal vertices in a tree is n minus 1 by 2. Why? Can you tell me? How many pendant vertices are there? Pendant vertices are n plus 1 by 2. If the graph has n vertices, okay, then p pendant vertices are there. N vertices were there and p pendant vertices are there. Okay. If I remove from the number of vertices, if I remove number of pendant vertices, then I am going to get number of internal vertices. From n, if I remove number of pendant vertices, then I am going to get number of internal vertices. So number of internal vertices is n minus pendant vertices, that is n minus 1 by 2. In fact, I can say number of internal vertices in binary tree, if I consider, then it is 1 less than the number of pendant vertices. In binary tree I am mentioning, this is in general for in any tree, but if I consider a binary tree, the number of internal vertices is 1 less than the pendant vertex. And one more type of graph, that is labeled graph, a graph in which each vertex is assigned a unique name. Just like we are naming the vertices, no? If in any graph all the vertices are labeled or named, then such graphs are called labeled graphs. Number of labeled trees, okay, with n vertices is n power n minus 2. This is just a note. You should remember, we are naming the vertices. Even in tree, if we do that, then it becomes a labeled tree. If T has got n vertices, then how many ways we can draw tree? In many ways I can draw. So that is nothing but many number of labeled trees I am getting. And how many such labeled trees exist if I have n number of vertices in my tree? That is n power n minus 2.